When installing a subpanel in a detached metal garage, it's crucial to understand the proper grounding and bonding techniques to ensure electrical safety and compliance with the National Electrical Code, or NEC. Since you are running a 4-wire feeder with separate ground and neutral conductors from the main panel in the house to the 100 amp subpanel in the garage, the grounding at the detached building must be handled correctly. Firstly, let's address the grounding electrode system. The NEC, specifically Article 250, provides the requirements for grounding and bonding. In a detached building supplied by a feeder, you are required to establish a grounding electrode system. This system typically involves driving one or more ground rods. The code mandates at least one grounding electrode, but two are often recommended, and in some cases required, to ensure a low impedance ground path. If using ground rods, they must be at least 8 feet in length and spaced at least 6 feet apart. It is also acceptable to use other types of grounding electrodes, such as ground rings, concrete encased electrodes, or underground metallic water pipes. However, for simplicity, we'll focus on ground rods here. Secondly, consider the connection to the building steel. The NEC permits the metal frame of a building to be used as a grounding electrode if it meets certain requirements. Specifically, if the metal frame is effectively grounded, it can serve as part of the grounding electrode system. An effectively grounded metal frame is one that is connected to earth by methods outlined in the NEC, ensuring a low impedance path to ground. However, simply bonding to the building steel doesn't automatically make it an acceptable grounding electrode. You must still comply with NEC requirements for grounding electrodes. Thirdly, understand the bonding requirements. Bonding refers to the connection of non-current carrying metal parts to create a low impedance path for fault current. In your situation, you must bond the metal building to the grounding electrode system. This involves connecting the metal frame of the building to the ground rods with a bonding jumper. The size of this bonding jumper is determined by NEC Table 250.102 C1, based on the size of the feeder conductors. This bonding ensures that any fault current will have a path back to the source, allowing the overcurrent protected device, such as the circuit breaker, to trip and clear the fault. Fourthly, address the connection to the subpanel. The grounding electrode system, which includes the ground rods and the connection to the building steel, if applicable, must be connected to the grounding busbar in the subpanel. This is typically done with a grounding electrode conductor. The size of this conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors, or, in this case, the feeder conductors. It is crucial to keep the grounding and neutral conductor separate in the subpanel. The neutral busbar should be isolated from the panel enclosure, and only the grounding busbar should be bonded to the enclosure. This prevents neutral current from flowing through the grounding path, which can cause nuisance tripping and other problems. Fifthly, address the question of one rod versus two. While one ground rod might meet the minimum requirements of the NEC, it is generally better to install two ground rods. The NEC, in section 250.53, 8.2, requires that if a single ground rod has a resistance to earth of more than 25 ohms, an additional electrode must be installed. Measuring ground resistance can be complex and requires specialized equipment. Therefore, the easiest and often most reliable approach is to simply install two ground rods from the outset. This provides a redundant ground path and ensures a low impedance connection to earth. Install the two ground rods at least 6 feet apart and connect them to the grounding busbar in the subpanel with a continuous grounding electrode conductor. Sixthly, consider the concerns about parallel grounding paths. The concern about creating a parallel grounding path is valid. However, it is important to understand that the purpose of the grounding electrode system is to provide a path to ground for fault current, not to carry normal operating current. The neutral conductor is the primary current carrying conductor, and it should be isolated from the grounding system in the subpanel. By keeping the neutral and ground separate in the subpanel, you minimize the potential for neutral current to flow through the grounding path. Seventhly, think about the importance of proper sizing. It is important to properly size all grounding and bonding conductors according to the NEC. Using undersized conductors can create a high impedance path which can impede the flow of fault current and increase the risk of electrical shock. Refer to the appropriate NEC tables to determine the correct size for the grounding electrode conductor, bonding jumpers, and equipment grounding conductors. Eighthly, consider the local amendments and inspections. Check with the local electrical inspector to see if there are any local amendments to the NEC that may affect your grounding and bonding requirements. Some jurisdictions may have specific requirements for grounding electrode systems, such as requiring a certain number of ground rods or specifying the type of grounding electrode that must be used. The electrical inspector can also provide guidance on the proper installation techniques and ensure that your work meets the code requirements. Ninthly, contemplate using a ground ring. A ground ring is a continuous conductor encircling a building and buried directly in the earth. If you decide to install a ground ring, it needs to be at least 20 feet in length and buried at a depth of at least 2.5 feet. The minimum size for a copper ground ring is 2 AWG. A ground ring offers a larger contact area with the earth, potentially reducing ground resistance and improving the effectiveness of the grounding system. Tenthly, consider a concrete encased electrode or UFA ground. This type of electrode involves encasing a length of bare copper conductor within a concrete foundation or footing. This is typically done during new construction. If the metal building has a concrete foundation, and if the proper provisions were made during construction, this can be an extremely effective grounding electrode. 11thly, consider lightning protection. While grounding for electrical systems and grounding for lightning protection are related, they are not the same. If the homeowner is concerned about lightning strikes, a separate lightning protection system may be necessary. Lightning protection systems are designed to provide a low impedance path for lightning current to flow to ground, minimizing the risk of damage to the building and its contents. 12thly, let's review the steps in a concise manner. Firstly, drive at least one, but preferably two, 8-foot ground rods at least 6 feet apart. Secondly, bond the metal frame of the building to the ground rods using a bonding jumper sized according to NEC Table 250.102. C1. Thirdly, run a grounding electrode conductor from the ground rods to the grounding busbar in the subpanel, sizing the conductor according to NEC Table 250.66. Fourthly, ensure that the neutral busbar in the subpanel is isolated from the panel enclosure. Fifthly, bond the grounding busbar to the panel enclosure. Sixthly, connect all equipment grounding conductors from the branch circuits to the grounding busbar in the subpanel. 13thly, regarding the wire size, the grounding electrode conductor size depends on the size of your ungrounded service conductors or, in this case, feeder conductors. For example, if your feeder conductors are 1/0 AWG copper, you would typically use the number 6 AWG copper grounding electrode conductor. Always refer to NEC Table 250.66 for the correct sizing, considering the material, whether copper or aluminum. 14thly, consider the material. Copper is an excellent conductor and often the preferred material for grounding and bonding. Aluminum can also be used, but it must be sized appropriately, as it has a higher resistance than copper. When using aluminum, ensure that all connections are made with connectors listed for use with aluminum conductors and that an antioxidant compound is used to prevent corrosion. 15thly, think about surge protection. Installing a surge protective device or SPD at the subpanel can help protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. SPD are connected to both the grounded and ungrounded conductors and are designed to divert surge current to ground. 16thly, contemplate the equipotential plane. In certain applications, such as agricultural buildings, it may be necessary to create an equipotential plane to minimize the risk of electric shock to livestock. An equipotential plane is a grid of conductive material, such as wire mesh, that is buried in the floor or earth and bonded to all metal equipment in the area. This ensures that all metal surfaces are at the same potential, reducing the likelihood of a dangerous voltage difference. 17thly, remember the lock nuts and bushings. Use appropriate lock nuts and bushings when connecting conduit to the subpanel enclosure. This will protect the conductors from abrasion and ensure a secure connection. Use grounding bushings and bonding jumpers to ensure that the conduit is properly bonded to the enclosure. 18thly, torque the connections. Use a torque wrench to tighten all connections to the manufacturer's specifications. Over-tightening or under-tightening connections can lead to loose connections, which can cause overheating and electrical failures. 19thly, let's talk about the wire type. Use appropriately rated conductors for all grounding and bonding connections. Grounded electrode conductors must be bare, covered, or insulated. If insulated, they must be green or green with a yellow stripe. Equipment grounding conductors can be bare or insulated. If insulated, they must be green or green with a yellow stripe. 20thly, keep accessibility in mind. Ensure that the grounding electrode system is accessible for inspection and testing. Ground rods should be driven in a location where they can be easily inspected and tested. The grounding electrode conductor should be routed in a manner that allows for easy access and maintenance. 21stly, document everything. Keep a record of all grounding and bonding connections, including the size and type of conductors used, the location of ground rods, and the results of any ground resistance tests. This documentation can be helpful for future maintenance and troubleshooting. 22ndly, when in doubt, seek professional help. If you are unsure about any aspect of grounding and bonding, consult with a qualified electrician or electrical engineer. They can provide guidance on the proper installation techniques and ensure that your work meets the code requirements. 23rdly, remember electrical safety. Always work safely when dealing with electricity. Turn off the power before making any connections, and use appropriate personal protective equipment such as gloves and eye protection. 24thly, let's discuss the neutral ground bond at the main panel. Ensure that the neutral conductor is properly bonded to the grounding electrode system at the main panel in the house. This is typically done at the service entrance. The neutral ground bond provides a path for fault current to flow back to the source, allowing the overcurrent protective device to trip and clear the fault. 25thly, understand ground fault circuit interrupters, or GFCIs. Install GFCIs to protect circuits that serve receptacles in the garage. GFCIs are designed to detect ground faults and interrupt the circuit, preventing electrical shock. 26thly, remember arc fault circuit interrupters, or FSIs. Consider using FSIs for branch circuits in the garage. FSIs are designed to detect arc faults, which can be a sign of damaged wiring or loose connections, and interrupt the circuit, preventing electrical fires. 27thly, consider the conduit type. Use appropriate conduit for running the feeder conductors from the house to the garage. Rigid metal conduit, or RMC, intermediate metal conduit, or IMC, or PVC conduit are commonly used for underground installations. Ensure that the conduit is properly sized and installed according to the NEC. 28thly, we should think about the burial depth. Bury the conduit at the proper depth according to the NEC. The minimum burial depth depends on the type of conduit and the location of the installation. Refer to NEC Table 300.5 for the correct burial depth. 29thly, use expansion fittings. Use expansion fittings on long runs of PVC conduit to allow for thermal expansion and contraction. This will prevent the conduit from cracking or buckling. 30thly, seal the conduit. Seal the ends of the conduit to prevent moisture and debris from entering. This will help protect the conductors from corrosion and damage. 31stly, label everything. Label all panels, circuits, and disconnects clearly and accurately. This will make it easier to identify and troubleshoot electrical problems in the future. 32ndly, we need to maintain it all. Regularly inspect the electrical system for any signs of damage or deterioration. Repair or replace any damaged components promptly. 33rdly, consider future expansion. When installing the subpanel, consider the potential for future expansion. Choose a panel with enough spare capacity to accommodate any additional circuits that may be needed in the future. 34thly, use the right tools. Use the right tools for the job. This will make the work easier and safer, and it will ensure that the connections are properly made. 35thly, let's check your work. After completing the installation, double-check all connections to ensure that they are tight and secure. Use a multimeter to verify that the grounding and bonding system is properly installed. By following these guidelines and consulting the NEC, you can ensure that the subpanel in the detached metal garage is properly grounded and bonded, providing a safe and reliable electrical system.